जी, तो आज हमारा वीडियो सेशन है। तो वीडियो सेशन में आज हम वही लॉजिक गेट्स पे बेसिस पे जो है वो डिफरेंट वीडियोस को वॉच करेंगे। मैं शेयर कर रहा हूँ आपके साथ, काइंडली उसको ज़रा व्यू करिएगा और कोई क्वेश्चन हो तो चैट पे आप पूछ सकते हैं, ठीक है?
What type of logic gate do we now have? What would you say? So let's compare it to the original NAND gate. So this would be A and B, and we would get A times B, but the complement of that result. Well, now we only have one input because both of these will be A. And so if we multiply these two, it would be A times A, and then we'll get the complement of that. What is A times A? Now you need to be familiar with some rules of Boolean algebra, and we're going to go over those rules soon. But A times A is basically A. One way to help you to see this is if you multiply 0 and 0, you get 0. If you multiply 1 and 1, you get 1. Now keep in mind, we're dealing with binary numbers. And so in a binary system, it works out to be true. A times A is A. So this is the same as the complement of A. So notice that we went from A to A prime. This is the equivalent of a NOT gate. So that's how you could use a NAND gate to make a NOT gate. So these two are functionally equivalent. Now, let's understand how
सर
this
रिजल्ट नहीं
works.
आया अब तक सर।
Truth table. So let's write the truth table of a NAND gate.
हाँ बेटा, रिजल्ट आ जाएगा, अभी वेट करो, आ जाएगा, ईमेल आ जाएगी, टेंशन नहीं लो।
सर दुआ कीजिएगा सर बस।
मैं इंशाल्लाह बेटा अभी बैठ गया हूँ मसल्ले पे आपके लिए।
Now,
इंशाल्लाह।
once we connect the two inputs together, let's say once we make this circuit, here we have this circuit, by the way. These two columns has to be the same. So therefore, these two possibilities cannot work. Because let's say if this is A, this has to be A as well. So meaning, let's say if we have a 1, we can't have a 1 and a 0. That's not possible. It's either, if this is going to be a 1, both of these inputs will be a 1. Or if we have a 0 here, both inputs will be a 0. So these are the only two possibilities. So if we have a 0, the output is a 1. And if we have a 1, the output is a 0. And so this is the same table of a NOT gate. Now let's talk about the OR and the NOR gate. The NOR gate is the complement of the OR gate, much in the same way as the NAND gate is the complement of the AND gate. And so let's draw the symbols for both of these. The NOR gate looks like the OR gate, but with a circle at the end. So given inputs A and B, the output of the OR gate, we said it's A plus B. For the NOR gate, it's going to be A plus B, and then it's the complement of that result. Now let's write out the truth tables. The OR gate, the output of an OR gate will be in the on state if either A or B is in the on state. Now, in the case of the NOR gate, it's simply the reverse. If either A or B is in the on state, the output will be in the off state. Now, one of the first things that you need to be able to do if you're taking a course in Intro to Logic Design is that you need to be able to write a function given a block diagram. So let's start with the first one in the upper left corner. The first thing I like to do is identify what type of logic gates I'm dealing with. So this is an AND gate. I'm going to use a capital A to represent it. Now, for the over here, notice that the inputs of the first AND gate are A and B. And when dealing with an AND gate, you need to associate it with multiplication. And when dealing with an OR gate, associate it with addition. So what the AND gate is going to do is going to take the two inputs and basically multiply them together. So the output will be A times B. Now the second AND gate will take this input, which is AB, and multiply it by this input, which is C. So thus we could say that the output of this entire circuit, represented by function f, is going to be the product of A, B, and C. So this is the answer for the first one. Now what about the second one in the upper right corner? Feel free to pause the video if you want to try it yourself. So let's begin by identifying each logic gate in the circuit. So we have two AND gates, and here we have an OR gate. So the output of an AND gate is going to be basically the product of the inputs. So this is just going to be x times y, and here the inputs are x and y prime. So this is going to be x, y prime. Now the OR gate is going to take the two inputs and then it's going to add them together. So the output of the OR gate will give us the function xy plus the other input xy prime. And so we could say that function f is equal to xy plus xy prime. So that's how we can write the function using or given a block diagram. Now let's consider the third one on the bottom left. So this is an AND gate, and so is this one, and here we have an OR gate. So when dealing with an OR gate, we're going to take the two inputs and add them together. So this is going to be A plus B. And for the AND gate, we're going to take the two inputs and multiply them together. So this is A times B prime. Now here we have another AND gate, so we're going to take these two inputs, multiply them together. So we may need to use a set of parentheses. So the function is going to be A plus B, so that's this input, times A B prime. You could put that in parentheses if you want to, but you really don't need to. Now let's focus on the last one. We have one AND gate and two OR gates. So for the first OR gate, we're going to take the two inputs and add them together. So this is going to be x plus y. And for the second one, we're going to do the same thing. So this is going to be x prime plus z. Now for the AND gate, we're going to take these inputs and then multiply them together. So in parentheses, we have the first one, x plus y, and then times the second one, x prime plus z. So f is equal to what we have here. Now here is a challenge problem. Go ahead and write the function given the block diagram shown below. Feel free to take a minute and work on this one. So let's identify the logic gates that we have. So here we have an AND gate, an OR gate, another AND gate, and then we also have an OR gate at the right. Now let's focus on the first AND gate. We're going to take the inputs x and y, and we're going to multiply them. Now for the OR gate, we are going to add xy with the other input z. So this will be xy plus z. Now for this AND gate, we are going to multiply these two together. So it's going to be x prime times xy plus z. Now, let's talk about the AND gate at the bottom. This is a 3-input AND gate. And the output of that AND gate is simply going to be the product of the 3 inputs. And so that's going to be x times y prime times z. Now the last thing we need to deal with is the OR gate. And this is a 3-input OR gate, and all we need to do is add the 3 inputs together. So anytime you're dealing with an OR gate, think of addition. When you're dealing with an AND gate, think of multiplication. So we could say the function f, the output of it, is going to be the first input, which is x prime times xy plus z, plus the second input, which is w, plus the last input, which is x, y prime, z. So this will give us the output of this circuit diagram using the inputs that we have here. So that's how you can write a function given a block diagram. Now let's work on the reverse. Let's say if we're given a function, how can we draw the block diagram? Let's say the function is ab plus c. Go ahead and draw the block diagram for that given function. So first, notice that a and b are multiplied to each other. So we're going to deal with an AND gate. And notice that we have an addition symbol. So we're going to use an OR gate between A, B, and C. So let's begin. Let's start with the AND gate. So here are the two inputs, A and B, and then the output of that will be just AB. Now we need to connect that with an OR gate. And then we need a new input, input C. So the OR gate will take the sum of these two inputs, and so we'll get the output AB plus C. And so that's it for that example. Here's another function. Let's say we have f is equal to xy plus x prime y plus y prime z. So go ahead and draw a block diagram for that given function. So notice that here we have what is called a product term. So we're going to use a AND function for this product term. Here this is another product term. So we're going to use another AND function to connect x prime with y. And we need another one to connect y prime with z. So we need 3 AND logic gates. Now we could use one OR gate to basically add the 3 AND logic gates together. Because we have the plus symbol, or a sum, we need to use an OR gate. So this is going to be the first AND gate. And we're going to put x and y together. And so that will give us the output xy. And then we're going to use another AND gate. And we're going to have the inputs x prime y. And then another one. So this is going to be y prime and then z. Now we're going to feed these 3 AND gates into an OR gate. And so the output of the OR gate is going to be the sum of the 3 inputs. And so that's how we can draw a block diagram for this expression. Now something else that you need to know. This expression here is something known as an SOP expression, which stands for sum of products. XY is a product, as mentioned before, X prime Y is a product, and Y prime Z is a product. So we have three product terms, and we're adding them. So that's a sum of products expression. Now, another term you need to be familiar with is literals. So every variable that you see, whether complemented or uncomplemented, is a literal. So X is a literal, Y is a literal, X prime is 1. So we have a total of 6 literals in this expression. Now let's consider another example. So let's say that F is going to be A plus B prime, and then times A plus B plus C times B prime plus C prime. Go ahead and draw a block diagram. Now the last example was a sum of products example. This one is known as a POS, which is product of sums. This right here is a single sum term. The reason why it's a sum term is because you're adding A and B prime. So notice that we have a total of 3 sum terms, and we're multiplying each of those 3 sum terms together. So thus it is a product of sums expression. Now how many literals do we have in this problem? So we have 1, 2, 3, 4, 5, 6, 7. So there's a total of 7 literals in that expression. Now let's go ahead and draw the block diagram. Now, for a sum term, should we use an AND logic gate or an OR logic gate? What would you say? Now remember, you want to associate OR with addition or sums, and you want to associate AND with multiplication, or basically products. So because we have a sum term, we're going to use an OR logic gate for each one. So we're going to need 3 OR gates, and we're going to feed these 3 OR gates into a single AND gate because we do have multiplication here. So let's go ahead and draw the diagram. So let's start with our first OR gate. This is going to be a 2-input OR gate based on what we see here. So the first input is going to be A, the second one is going to be B prime, and the output of this OR gate will be A plus B prime. Now moving on to the second OR gate, it's going to be a 3-input OR gate. The inputs will be A, B, and C. The output is going to be A plus B plus C. And for the last OR gate, this is a 2-input OR gate with the inputs B prime and C prime. So this is going to be B prime plus C prime. Now let's feed these 3 OR gates into a single AND gate. So the output of this AND gate is going to be the sum, not the sum, but the product of these 3 expressions. And so you just got to multiply them. Thus is going to be everything that we see here. So I'm not going to write it again. And so this is the block diagram for the function f. Now let's work on number 3. Describe each of the following expressions as an SOP expression, sum of products, or POS expression, product of sums, both or neither. And at the same time, discuss the number of variables, literals, product terms, and sum terms, and identify any min or max terms. So let's start with this one. Let's say we have the expression xy prime plus xyz prime plus x prime yzw plus xy prime z prime. So is this a sum of products expression or a product of sum expressions? Or is it both or neither? So this is a product term. Each one of these are product terms. Now, just to review, one literal could be a product term. So x is a product term. Y prime is a product term. Or if you multiply them, these are product terms. So what we have here is a sum of products expression. We have 4 product terms, and as we can see, there's a plus sign separating them. So it's a sum of products expression. Now, how many different variables do we have in this expression? Notice that we have x, y, z, and let's not forget w. So we have a total of 4 different variables. Now, how many literals do we have? So here we have 2 literals. It could be complemented or uncomplemented. Here we have 3 literals. This has 4, and then this is 3. So if we add them together, there's a total of 12 literals in this expression. Now, what about if we have a min term or a max term? What would you say? In this case, since we're dealing with an SOP expression, a sum of product expression, we need to identify the standard product terms or the min terms. Now, a midterm is basically a standard product term that includes each variable of the problem. So it has to include all 4 variables, either complemented or uncomplemented. So this term right here is the min term in this expression because it has all 4 variables. Now let's move on to our next example. Consider this expression, x plus y times x prime plus z, and then times y plus z prime times x plus y plus z prime. So is this a sum of products expression or a product of sums expression? So x plus y, this is a sum term. X prime plus z is also a sum term. So notice that we have a total of 4 sum terms, and each of them are multiplied to each other. So this is going to be a product of sums expression. We have the product of 4 sum terms. Now, how many variables do we have in this expression? So I see 3 variables, x, y, and z. Now, how many literals are there in this expression? So here we have 2 literals in the first sum term. The second sum term has 2 literals. The third one has 2. And the last sum term has 3 literals. So thus we have a total of 9 literals in this problem. Now, we're not going to have any min terms because this is not a sum of product expressions. But we do have a max term because this is a product of sums expression. So what is the max term in this particular problem? So which sum term includes each variable of the problem, either complemented or uncomplemented? So this is the sum term that has all the variables. So therefore this is considered the max term. Now let's move on to our next example. Let's say we have the expression xy prime zw. So this expression, is it an SOP expression, a POS expression, both, or neither? What would you say? It turns out that this is both a sum of products expression, and you could describe it as a product of sums expression. So in terms of, let's say, SOP, we could say that this is the sum of one product term. Now, in the case of a POS expression, you can also describe it as the product of 4 sum terms. Now, if that statement confuses you, see it this way. X, you could think of X as X plus 0. Y prime, you could see it as Y prime plus 0. And then Z plus 0 and W plus 0. Now, in this form, it looks more like a product of 4 sum terms. At least that's one way I think of it. But that particular expression can be described as both a SOP and a POS expression. Now, how many variables do we have? And how many literals? So for this expression, we have a total of 4 variables: W, X, Y, and Z. We also have 4 literals: W, X, Y prime, and Z. So that's all we could say about this expression. Let's move on to our next example. Consider the expression A plus B plus C prime plus D plus E prime. So can we describe this as an SOP or POS expression? Like the other example, you could represent it as both POS and SOP. So as an SOP expression, we can say that this represents the sum of 5 product terms. And as a POS expression, we could say that this represents the product